Physics is the least applied of the sciences, so it typically feels the most disconnected from reality. However, there are many fields in high-level physics that make large impacts on our day-to-day life. Smartphones rely on computer chips, which rely on transistors, which rely on quantum field theory. Digital cameras use quantum mechanics to detect when a photon hits a special type of computer chip, which is also a transistor and therefore relies on quantum field theory. Every giant advancement in the quality of life of human society has been preceded by a breakthrough in physics, from Archimedes discovering density measurements to Alan Turing building the first computer. Now, a new field that offers similar technological advancement is newly born and ready to be discovered. Quantum dots are like customizable atoms, where we get to decide exactly what kind of properties we want in a material. To understand how quantum dots work, you need to know how they're made. A quantum dot is a super small crystal structure. The core is responsible for many of the properties of the dot, while the shell and ligands will determine their chemical applications. The ligands, stalactite-like formations on the surface of the dot, determine how soluble they are in different liquids. Some ligands make quantum dots soluble in water, others make them soluble in oil. By choosing what core, shell, and ligands are used in the dots, the properties of the dot can be fine-tuned. The most characteristic property of quantum dots is how they interact with visible light. When incoming light hits a quantum dot, it is absorbed and re-emitted. When it's re-emitted, however, it looks very different from when it was absorbed. The light that comes out of the dot will always be the same color, because the color is determined by the frequency of the light, which is in turn determined by the size of the dot. This property of quantum dots is a direct result of how small they are. Their size is what makes them quantum. A normal material is a big chunk of various atoms in a semi-regular arrangement. As incoming light is absorbed, it can be re-emitted at any one of a number of frequencies, with more frequencies being available with higher energy light. A quantum well reduces the dimensions of a bulk material to only being two-dimensional. This results in an interesting range of frequencies that look like a staircase. There's some threshold energy that, if surpassed, will allow for a specific increase in the possible frequencies. This idea is similar for a one-dimensional material, but using a zero-dimensional material is a recent idea. A zero-dimensional material doesn't have a range of frequencies at all. In fact, it only has a set number of allowed very specific frequencies. This makes the light that comes from a quantum dot very pure and bright. So they were originally used in TVs to make difficult colors like yellow. Now we see that they could have many potential uses with enough experimentation. The frequency of emitted light from the quantum dot is most easily determined by their band gap. The band gap is roughly related to how conductive the material is, and normally it is a definite quantity that's determined from the number of protons in the nucleus of the atom. However, with quantum dots, the band gap is determined by their size and structure. This incredibly useful quality is exotic and strange in comparison to most materials. Imagine if, as you made a snowball, the larger it got, the redder it became. And then, if you scraped some of the snow off, it would start to turn blue. The only structure in the normal world that behaves like this is a jawbreaker, but in the quantum world there is a massive wealth of materials that can be used.